Welcome to our unit. For this packet, we talked about a few things, starting with what is matter and ended with what is going on with density. So in this video, we will quickly go through the notes. I will also include in our Google Classroom a snapshot of our notes page so that you can make sure that your notes page looks like mine. So here we are, Unit 1A Notes. In this unit, we started off talking about matter. And we did a card sort so we could explore what is matter and what is not matter. The definition that we came up with / got from the textbook for matter is anything that has substance and takes up space. Takes up space. Now, there is a more scientific way of phrasing this. Let's get this back in focus. There's a more scientific way of phrasing this, which is anything that has mass and has volume. Right? So these two important terms, mass and volume, are how we determine whether or not something is made of matter. Now, sometimes that can be a little tricky. You might have things like air, for example, which at first glance or first thought, you might think, oh, does that have a volume? Does it have a mass? Can you weigh air? You can, actually, right? You can imagine filling up a balloon with air, right? That balloon is the mass of the balloon, but also the mass of the air inside. It has a volume, right? You can actually measure the volume of gas or air inside that balloon by measuring the volume of the balloon. Now, you can also know that air has mass by thinking about different altitudes. So if you are close to sea level, the actual atmospheric pressure, the amount of weight the air is putting on you is a lot higher than if you were to go up to the top of Mount Everest, because there's less air. The thickness of the atmosphere is less, so the air is putting less pressure on you on the top of Mount Everest than at sea level. So it does have a mass. So after that, after talking about matter, we talked about some measurements. We talked about two very important measurements, which are mass and volume. The mass is, so we see the next vocab word down here. Mass is the measurement of the amount of matter in an object. Now we see that these two definitions for matter and mass do reference each other, which is a little annoying. I don't like it when that happens. But that is how we define mass. Now, mass is measured in the unit of grams. But we also use kilograms a lot in this class. Which is abbreviated kg, and you can also add in here like the 1,000 grams equals 1 kilogram if you wanted. Next, we talked about the word unit. So unit is not a word that we would typically go over, but I think it's nice to have a formal definition for it. I think the idea of a unit can sometimes be hard to define, and so it's nice to have a formal definition. So a unit is a standard for making comparisons between measurements. Making comparisons between measurements. Now, these are made up, right? Units are something that humans have created to help make sense of our world. They are not some like fundamental truth about the universe. You could make up your own unit for something, right? You could make up your own unit for length. Maybe you want to measure everything based on, I don't know, the length of your pinky finger, right? You could make up your own measurement for length. But we have a series of units that we use in science, and we'll talk about those in a minute, called the International System of Units, or Système International. And we all agree on to use these specific units in science class and in the practice of science. So these comparison between measurements. Let's go ahead and finish writing. So some examples of units, right, would be like inches and like centimeters, right? Even something like we would use for measuring time, like seconds or days. A day is a unit. Lastly, we did the definition volume. So volume is the measure of the amount of space that something occupies, right? The amount of space that matter takes up. So we're thinking about three-dimensional space. So you probably learned how to calculate volume of different types of three-dimensional shapes when you were in middle school, or even in geometry. That's something that you might have reviewed. So you might have learned formulas like volume is equal to length times width times height, right, to measure the volume of a rectangular prism. You might have learned about measuring the volume or calculating the volume of a sphere or a cylinder or a rectangular prism, right? These are all, you might have had a couple formulas for these before. Now, the unit for volume, we have a few different units for volume that we use. We predominantly use cubic meters. Or like some variation on a cubic meter, right? Like centimeters cubed equals cubic centimeters. Or we use the liter, it's abbreviated in L, or like the milliliter is also really common, ml. Now, one thing it might be nice to note is that 1 centimeter cubed is equal to 1 milliliter. These are two different ways we can represent volume. The centimeters cubed is often when we're measuring like a solid. If you're using a ruler, you would use centimeters cubed. If you're using a liquid, if you're measuring the volume of a liquid or a gas, you probably are going to use the liters or milliliters. However, right, you can convert between them because 1 centimeter cubed is equal to 1 milliliter. Fun. All right, so we are going to come back to these remaining definitions after we go over our making measurement notes. What I'm going to do is I'm going to do all the things we need for this packet, all of the notes. I'm going to do this in one video so that you can kind of go through and review what you need. All right, so next we're moving on to the making measurements section. Let's move this down. Now, when we were talking about making measurements, we had a few key things that we talked about. The first thing that we talked about was that scientists use a specific type, a specific set of measurements, a specific set of units when reporting data. So scientists use SI units. The SI stands for System International, and this is a French organization, hence the fancy sounding name. When we use these when measuring anything, right? We could be measuring time, we could be measuring length, we could be measuring temperature, right? There are specific sets of measurements that we use. And they are not necessarily the measurements that we use in the United States to measure the same things. Some of them are the same. We use the same measurements for time. But for the others, it might be a little different. So you can find these SI units on the next page of your packet, right? Right here in the units reference guide. So we have for time, distance, temperature, mass, volume, amount of matter, right? We have these units that we use. Now you'll also have some other common units, right? These are other ones we might use in class. So there's a few variations on those, so you have those available to you. Also, these units in science, right? We have these units that we use. We also sometimes change the size of that unit by using a prefix. So this tells you the power of 10 that unit is at, right? So a kilogram, right? The kilo part means 1,000. So a kilogram is actually equal to 1,000 grams. Just like a centimeter, right? Centi is right here on our prefix chart. It's right here, centi. It means 1/100th. So you need 100 centimeters to equal 1 meter. We'll go over that more at another time. So next we have, for our next note on making measurements, we have this. A measurement is always made up of two parts. A measurement, let's spell this correctly, is always made up of two parts, right? And I'm being explicit about this, even though it seems kind of obvious, because a lot of times students will remember that you have to include the value of the measurement and unfortunately forget to include the unit. So anytime you have a measurement, if you do not include the unit, it is no longer a measurement. You need the unit in there to provide context. So it has the number and the unit, right? So if you had a measurement of 25 centimeters, but didn't include the centimeters part, you wouldn't know how to compare that measurement to something else, right? You don't know if you have 25 centimeters, 25 meters, 25 elephants, 25 light years. You don't know what that number means without the unit. So even if I know what you're getting at, well, I have some assumptions about what you're getting at, you do need to always include the unit, because you can run into some pretty bad mistakes if you don't. Okay, so lastly, our last thing on here is the last digit of a measurement is always estimated. And this is another thing that students get really tripped up on, that they can run into some problems. So the last digit of a measurement is always estimated. Now, I'm saying this, I'm sharing this with y'all because it's important to think about the precision and accuracy of your measurements. And the number of digits in your measurement tells you how accurate and precise your measurement actually is. Because because it reflects the actual accuracy and precision of your measurement tool. So we're going to look at a few examples of this to help you out thinking about number 3. Okay, so on number 3, we have these 2 pictures here. And we're going to, right underneath number 3, we have these 2 pictures. And we're going to do these 2 things together quickly. And then I think we're about done with our notes. Yay. I will actually end up doing, I think, another video on density just to help you out with that, since that is on a separate piece of paper, for those of you who got that paper. All right, so let's do this ruler first. So in this ruler, we see it says centimeters. So this is measuring the quantity known as distance, right? We are measuring distance when we're using a ruler. And our abbreviation for centimeters, right, of course, is cm, centimeter. All right, so what we're going to do is we're going to take a look at this black bar and figure out how long it is. So what we see here, right, it's lined up nicely at 0, and we can see it goes all the way to, like what, here? Yeah, here. So when we're recording this measurement, we are going to look at all of the tick marks. We'll start off with the big ones because these will represent a larger value, and then we'll use the smaller tick marks to get more precise. So what we see here is we know that our measurement, our first measurement, is at least 3 centimeters, right? Because it is in between the 3 centimeter and the 4 centimeter mark. So we know that the first digit in our measurement is a 3. Now, if you just said that, oh, this bar is 3 centimeters long, that is incorrect, because it is actually longer than 3 centimeters, and our measurement tool that we have available to us allows us a greater level of precision than just saying 3. So we can all agree that this is a 3, right? This is something that we know. We know that that is a 3. Okay, that first digit, it's at least 3 centimeters long. So let's go a little bit deeper in this measurement, and let's look at the smaller tick marks. Each of these smaller tick marks, right, this right here, represents 0.1. And we know that because we can actually count the number of tick marks in between each measurement to get that, that value. So if we have 10 spots, 10 little jumps to make between 1 and 2, that means that each of those is worth 0.1, right? Because we go 1.1, 1.2, 1.3, 1.4, etc. So let's use that same idea up here and figure out if we can get more precise than just 3. So this is 3.1, 3.2, 3.3, 3.4, 3.5, 3.6. All right, so I think we can get this level of precision a little bit higher. So now we have made it down to this distance. So we know now that it isn't just 3 that we know that it's also at least 3.5, right? 1, 2, 3, 4, 5, right? It's at least 3.5 centimeters long, this black bar. Now, many people would stop right here and be done. However, the last digit of the measurement is always estimated, right? And if we were looking at this, just 3.5, that would mean that this one was estimated. But that's not true, right? We know it's at least 3.5. We can tell based on the tick marks, right? It's not 3.2, it's not 3.9, it is 3.5, it's between 3.5 and 3.6, right? So that's a known number. We know it is true because we can read it on the tick marks. So this is where our estimation comes in. We are going to estimate one more digit. So looking at this here, we can see where it falls in between these two lines. this estimate, your estimate can be any number, between 0 and 9, right? We could say this is 3.50. We could say it's 3.59. We could say it's 3.54, right? Everyone might read that last digit a little bit differently. And that's okay, right? Because that last digit is estimated. So I'm going to say this is pretty close to halfway in between. It looks a little bit closer to the 3.5 than the 3.6 to me. You might read it differently, and that's cool. But I'm going to say that it's 3.54, right? And that is my estimated digit, right? If you put a different digit in the hundredth place than I did, that's okay, right? Because that's an estimate. You do want to try and get as close to what you believe is the real number as possible, right? So if that line is like really close to like 3.6, right? We wouldn't want to put 3.50. That would be inaccurate. We want to try and estimate it as close to the real number as possible. But again, right, your estimate could be 0, right? If it's right on the line, if it's right on the line of 3.5, you might say 3.50, right? That would be a valid estimate. You could even say maybe your estimate is actually, it looks like it's right on the line, but it's a little towards one side of the line, right? Maybe you say 3.51 or even 3.49, right? Those are still valid estimates. Okay, so the last thing we want to include in our measurement is our unit, right? Because a measurement is always made up of two parts, the number and the unit. So we have our number for our measurement, and we just have to include our units. Centimeters. Yay. Okay, so let's do the next one. The graduated cylinder. Graduated cylinders measure volume. And in this case, we're using the unit of milliliters. When we're using a graduated cylinder, we want to look at this curved line here. This curved line is called the meniscus. The meniscus. And when you are looking at the meniscus to determine our volume, you always want to look at the bottom of the meniscus. So you want to read your volume from the bottom of the meniscus. Now, when you actually look at the meniscus IRL in real life, you're gonna see what looks like it looks kind of like a lens right here. It looks like this kind of thicker, shiny bit because of the water level, like the water reflecting off of itself. So it can be kind of hard to see sometimes. You want to look at the bottom part though of all right. So let's look here at this meniscus right here, and we're going to figure out what the volume of liquid is in this graduated cylinder. And it's kind of hard to see these numbers, so I'm just going to write them a little bit bigger. So we know, based on the position of the meniscus, that this volume in this graduated cylinder is someplace between 2 and 3. Let's make this 3 a little bit clearer. Right? So our first digit, right, in our ones position, we're not going to use our tens position. In our ones position is going to be a 2, right? Because we know that it is at least 2, but it is not 3. So next we're going to start looking at our tick marks. So from here, right, this is our line for 2. We're going to count the tick marks until we get to where the meniscus is. Now we can also see between the line representing 3 and the line representing 2, we have 10 tick marks. That means that this distance right here is going to be 0.1. Okay, so let's count our tick marks. So we have 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7. All right, so now we see that our value is going to be in between 2.6 and 2.7. So that means the number we're going to put in our 10th position is 2.6. All right, so this is our known number, right? This is the number that we know based on the measurement tool, right? We have lines that represent those places in our measurement. Now, the hundredths, we don't have a smaller tick mark to represent the hundredths. So that means that that is going to be our estimate. Now, many students will stop here, like 2.6, good enough. No, estimate, right? Your estimate can be between 0 and 9, right, depending on where the measurement is, right? It's up to your interpretation. So if we look at this, we see our two lines representing 2.6 and 2.7. We want to look at this line in the middle where our bottom of the meniscus is, and we'll estimate what we think that number is. This time, I'm going to go with my estimate being 5. So we got a number of 2.65. Now, our last thing we need to do, of course, is our units, which are milliliters. Okay. All right. So we'll do one more thing on here just because we're already on here, and that is include a definition for density. All right, so we're going to go up and add our definition for density in here while we are doing this. Okay, so density, the definition of density is our last thing on here, and then we're going to wrap this up. Our definition of density is the degree of compactness of a substance, meaning how closely packed together the mass of a substance is. So is there a lot of space in between the particles of the substance? Is there not a lot of space? Is it heavier per unit volume? Is it not as heavy per unit volume? That's one way to think about it. So the alternate definition is the measure of the mass per unit volume. So its units are usually compound units, meaning that units are made up of 2 units, a unit for mass and a unit for volume. Now I'm just going to give you some examples, okay? So grams per centimeters cubed is an example. Grams per milliliters is an example. Grams per kilograms, kg over L, kilograms per liter is an example, right? These are all examples of density. Now I'm just going to write over here quickly the density formula. Density is equal to mass divided by volume, and we'll have more on that later. All right, so those are the notes for Unit 1A. One thing to think about is on the back we have 2 methods of measuring volume: length with height and water displacement. This is a good thing to review quickly. And then on the back we also have our unit reference guide, which will also be really useful. All right, I will talk to you next time.